Okay, good morning, everybody. Okay, welcome to Papa Lim Physics Classroom. Okay, today we'll be looking at one of the paper that I have set for my 4N A students. Okay, the mid-year paper that they have just did recently. Okay, if you want to try out the paper, I leave it in my Google Drive. Okay, the link is at my description below. You can access it and take a look at it. Okay, you have already done it and you want to check answer. Okay, remember you can scroll the timing, scroll the video to a certain portion that you want. If you want question 6, just scroll to question 6. Okay, don't watch through the whole video if you don't need it, because the video is going to be a very long one. Now, for the paper, if you've done the paper, okay, I will show you this is the MCQ answer for paper 1. Okay, if you might want to pause the video and record down the answer first. If you have done it, okay, I will be going through each of the questions in detail, and you can just look at which questions you make a mistake, or it could be a careless mistake, or it could be something that you actually don't know. Okay, let's hope that after going through the paper, you will actually have some details about the concepts or some of your misconceptions that you might have. Now, for question 1, right? Question 1, I would say that most of the students I've seen, okay, they do know how to read the Vernier Caliper. Okay, so but just to be on the safe side, if you have forgotten how to read the Vernier Caliper, okay, I have actually uploaded a video on it in my chapter 1 video. Okay, under my chapter 1, there's a section of it on Vernier Caliper and how to read it. Okay, so please be familiarized with the two main instruments, the Vernier Caliper and micrometer screw gauge. At the question 2, okay, know how to read them. Now, for question 1, right, if you know how to read them, you will know that the answer given or from the diagram would be actually what I call 1.0, okay, followed by 6, 5, 6, 7, 8, okay, with 8 cm. Okay, so if you read from the diagram, it'll be 1.08. The common mistake that I have is the students actually did not read the question clearly. The question asked for 1 layer of plastic, but the diagram given 1.08, it actually refer to 5 layer of plastic. So 1.08, okay, which is option C, is not the answer. 1.08 cm is only for 5 layer. So if I need 1 layer, I will need actually to divide the answer by the readings by 5 to get the answer specifically. So after dividing, you will get the answer to be 2.16 mm, or what I call 0.216 cm. Okay, so that will be answer for question 2. For question, that will be answer for question 1. For question 2, the reading of micrometer screw gauge. Okay, I will not say there isn't any booby traps or anything new about it. It's just a pure basic of reading micrometer screw gauge. So you have to be familiar with it. Now for question 3, right? Question 3, the question asks for average speed. This type of question usually has 2 variations. They will actually ask for average speed, okay, and sometimes they will actually ask for average velocity. Okay, I will look at it, each of the section in detail to see how you're going to solve it. If you look at average velocity, average speed, okay, average speed, the formula we are looking at is total distance divided by total time. Okay, so the total distance here we are talking about, the total distance I'm talking about here refer to the actual distance traveled. So actually from P to T, okay, I actually traveled the actual distance 10 km, 5 km, 10 kilometer, and 5 kilometer. So literally for total distance, I actually need to add up all the distance I travel. So literally I have to add up, okay, 10 km, okay, 5 kilometer, 10 kilometer, and another 5 kilometer. That will be the total distance I have. And the time taken based on the question is 30 minutes, which is actually 0.5 hour. Okay, if you substitute the numbers into your calculator, you actually get the answer straight away. You actually get the answer to be 60 kilometer per hour. Okay, I will not say it's difficult, it's something quite standard, I would say. But when we talk about average velocity is different between average velocity and average speed is actually the numerator, which is the total displacement. Instead of distance now, I need now is total displacement. Displacement, what we are looking at is actually the shortest distance between the start point and the end point. Okay, usually I'll just locate the start and end point, and I will just draw a straight line between them. That would be what I call the displacement line. Okay, so between these two lines, okay, between these 2 points, I'll draw a straight line, and that line will actually be my displacement. Okay, and that will be the total displacement traveled by the car itself. Take note, for total displacement, right, it may or may not be the actual distance traveled by the object. Okay, the definition for displacement is actually the shortest line between the start and end point. Okay, so students, if you look at average velocity, okay, we are looking at the displacement as in the shortest distance between the 2 point start and end point. Yeah? So if you compare to average speed, we are talking about the total distance. Yes, it's also between the start and end point, but total distance refer to the physical distance traveled between the start and end point. So literally the numerator that you're going to get, it will be different number in some of the cases. Okay, so please take note of it. Question 4, okay, not a positive effect. Okay, I would say it's quite straightforward. Most of the students are able to actually get the correct answer for it. Okay, so just to take note, for skydiver deploying their parachute to slow down their descent, this is definitely a positive effect. I need the air resistance to slow me down. If not, I will actually smash onto the ground or land onto the ground at a very, very high speed. Okay. For question 5, I would say just read. You have to read the picture carefully. Some of us, we have the idea, we have the conception that the numbers actually read from the below, from the bottom up. Okay, so instead of like you telling me the answer to be 1.7 from the picture here, you actually do a simple 2.5 minus 1.7. Okay, which you thought, which could be that you thought the answer actually referring to the lower section of the scale, which is not. Okay, remember when we look at the diagram, we look at the scale, we always like to read from the 0 scale. Doesn't mean I have to read from bottom up. Look at where is the 0 marking. The 0 marking is at the top. Okay, so for this scale is actually, I'm actually reading from the top downwards to the bottom. Okay, so if you look at it carefully, you count the marking carefully, it will be actually 1.7 Newton. Okay, how do I know it's in terms of kg or mass? Okay, partly because the scale here say newtons. Okay, the scale here say newtons, so this is actually a spring balance, okay, which measures stuff in newtons. Question 6, question 5, question 6. Question 6 is a midpoint. It's a object balance at midpoint. Now we have 6 Newton and 4 Newton. Okay, pivot at midpoint. This is the midpoint, which means I can safely say that the left side is 4 meter. Midpoint means the other side will be also 4 meter. Okay, so this is an 8 meter beam. It's a long beam. Okay, but it doesn't mean that I'm going to use both 4 meter in my working. No. Okay, take note, because for moments we are always looking at the force that I'm interested in, and the perpendicular distance I'm always looking at is always measured from the pivot, okay, to the force himself. Okay, it's the perpendicular distance from the pivot to the force. It's not like whatever distance of beam I have to use 4 meter because the beam is 4 meter. Okay, it doesn't work this way. Moments, we are looking at the formula. Remember, the idea of moment is force on perpendicular distance, and the idea of perpendicular distance refer to actually is measured from the pivot to the force itself. Okay, so always remember this condition for moments. So after that, what you do, you will know that for force F, okay, it will be a clockwise moment. I will label it MF. For 6 Newton, it will actually be a anti-clockwise moment, M6. Okay, and likewise for 6 Newton, the perpendicular distance will be 4 meter. Now, so same thing, if it is balanced, okay, based on the question, it is balanced. Balance means one thing, it means the anti-clockwise moment is equal to the clockwise moment. Okay, and so which means you straight away you will know that the moment F, MF, must be equal to the moment's anti-clockwise moment M6. M6, if you break it down, it will be 6 Newton multiplied by 4 meter. M4, you break it down, it will be force F multiplied by, not 4 meter, it's 3 meter, okay? Perpendicular distance is 3 meter. If you let your algebra do the work or do the magic, you will have F equal to 24 divided by 3. You will have 8.0 newtons straight away. That will be the answer for question 6. Okay, so take note of the perpendicular distance. Yacht. Okay, question 7, yacht. Okay, moving at certain speed. Okay, take note now when you look at formulas calculation in physics, make sure I would say 90% of the formulas require the factor, all the variables to be in SI unit. So a common trick that we always like to play with the question would be like with numbers. Is we actually give, instead of meter per second for speed, I will give you in km per hour. If you see your speed to be represented in km per hour, remember to convert it to meter per second. Likewise for mass, if you have kg, okay, that's the unit I want. Sometimes I will give you grams, so you have to convert to kg. Okay, for kinetic energy, that will be the standard formula. You have to remember Ek equal to half mv square. Okay, what you do, just substitute all the values inside, 5,000. After that, let your calculator do the work. Okay, you will get the answer, okay, the correct answer appearing in your calculator. Okay, question 7, which is actually to be 40,000. Okay, so take note of the formulas, take note of the condition. For calculations, most of the time we actually require SI unit. Okay, question 8. Okay, after 5 swing, he swing freely, and he realized that after 5 swing, he start to slow down. Or to be exact, after every swing, he start to slow down. Okay, so this is one classic example whereby air resistance is actually present in the question here. Okay, which is correct. Okay, read the question carefully. A lot of the students choose A straight away because A is the correct answer, which is correct. But it is wrong in this case because the question is asking for a false statement. Which of the following statement is false? Okay, so read the question carefully. Okay, and you'll find that definitely straight away, if you know there is a false statement, you will definitely know that, okay, B will definitely be the answer. Okay, law of conservation of energy, okay, is always obey. Okay, conservation of energy is always obey. Energy cannot be converted, or it cannot be created or destroyed. It can only be converted from one form to another form. It always okay, energy is always translate or change from one form to another form through different transformation. So it has to be obey. It has to obey. Okay, so literally you know that part B will be the answer. It will be a false statement here. For question 9, question 9 is the attraction between particles, different state. I would say it's quite straightforward because it actually resonates with what is being taught in chemistry. So most of the students actually got this correct. To be exact, I think every student got this correct. 9 and 10, okay, same thing. When you talk about liquid, you're talking about fixed volume, a object being able to slide over each other, or the intermolecular bonds is like, I would say it's strong, but it's not very, very strong. Okay, so most of the students actually know that when we are talking about different no fixed shape, okay, I'm actually talking about the particles being able to move within the liquid, being able to restructure their positions and their shapes. Question 11. Question 11 is a transfer of heat, or I say a radiation question. How do I know straight away is radiation? Because the questions actually ask for one factor, which is silver versus black. What we are looking at for silver and black, okay, I'm looking at the color. And color, if you look at transfer of energy, absorption of energy, transfer of energy that deal with color is only one factor, what we know as radiations. Okay, so these are the clues that's given in the question to tell students to actually narrow down on like which topic of the syllabus I'm testing. Okay, for heat transfer, this is definitely one of the topic. I think if I'm not in chapter 10, and which part of chapter 10 heat transfer am I looking at? If you look at silver and black, you look at color, it will definitely be radiation. That's why if you look at the keywords you have to use is either I'm using absorption or emission. Okay, and if you look at radiation, absorption, and emission straight away, okay, this information will give rise to one thing, whereby we always tell students to actually take note of the color. Black is always a good emitter, okay, and it's also a good absorber. Okay, so straight away you will know that which object absorb and emit more. Okay, if you know the clue, okay, you will know that the clue is actually telling you the answer. If you talk about radiation, black being a good absorber and radiator, means if I look at black, it has to absorb more. Black, it has to emit more. So straight away, you actually can narrow down on the answer to be actually A. Okay, straight away. Okay, because if you look at the fundamental, the concept of radiations, we always emphasize that black is always the best absorber and the best emitter. Okay, so if you know what you are doing, what are the keywords, you can actually solve this question actually within like 20 seconds. Okay, that's where you save time for other complex question. The next thing we look at is we look at convection current. Convection current, if you look at the moment you look at this term, a few things that must come to your mind. You talk about change in density, whereby you look at the flow, okay, the movement of the matter, the solid or gas, the movement, and that movement is actually governed by hot rise and cold sink. Okay, and remember, it's not just hot rise, cold sink. We have to actually mention about density. So if usually we will tell students when we talk about hot rise, you definitely have to write about the density, about less dense. And cold sink, you definitely have to talk about density. Okay, why is sink? Partly because it's denser. And lastly, okay, when we talk about radiation, when we talk about convection, there's always 3 points that you always have to write. If this is a structural question, you always talk about hot rise, cold sink, that's the first thing. And secondly, you always mention about the density, hot being less dense, cold being denser. And the third statement that you always write is you always tell students that I tell the marker that the convection current is being set up, or the convection current is being repeated. Okay. These are the 3 statements that we always tell students to write if you're looking at structure question. And for MCQ, for this question, we are actually emphasizing on the hot rise and cold sink. Okay, the cycle always look at hot rise. Okay, this is where the hot rise. And after that, we talk about where the cold sink. Okay, so if you look at the cycle here, okay, you will definitely see that if I want the hot rise, cold sink, if I want the convection current to occur in this particular format, my heat source has to actually to be at location B. So if I heat up at location B, my hot water will actually rise. And on the right side, my cold water can actually sink to actually replace the space that was previously occupied by the hot liquid here. So I will have the convection current set up in this particular setting here. Now for question 13, 13 is a basic example of what we call melting. Okay, so remember when we talk about melting, we are looking at the internal energy of the particle. Okay, internal energy of the particle. So if you have done your revision, you will find that this term is actually quite familiar to you. When the moment I talk about internal energy, I'm actually referring to 2 other energy. I'm talking about the kinetic energy, the internal kinetic energy, and the internal potential energy. Okay, and when we talk about kinetic energy and potential energy, in terms of what? In terms of melting. Okay, in terms of melting, okay, you definitely have one, or to be exact, you definitely have 2 phenomena, 2 specifications happening. When we talk about melting, first thing is the temperature actually remain constant. Okay, because the energy, the EK, actually remain constant. Okay, aka means the temperature actually remain constant. But then I will still be absorbing energy from I will still be absorbing energy. Where does energy come from? Where does energy go to be exact? Okay. In this case, the energy comes from the environment, but after absorbing by the ice cube, where does the energy go to? Okay, it goes to the potential energy, okay, which actually controls the change in state. Okay, how? Okay, by stretching the intermolecular bonds or intermolecular force between the particle. Okay, or weakening the intermolecular force, okay, in the liquid here. So that's why if you look at melting, okay, melting, the first characteristic is always the temperature. Temperature here always remain constant, which is C and D. Okay, and after that, what we're looking at is when the ice melt, okay, temperature remain constant, but at the same time, okay, the water, because the ice is melting, the water will actually be, temperature of the water will actually be reducing, okay, because the ice is melting, the temperature, and as a result of that, the water temperature actually decreases. Okay, so take note of your change in phases for your thermal property for when you are looking at heating, boiling, or even your melting. Okay, these are a few phases that we always look at. Now, question 14. Question 14, greatest kinetic energy. Remember, like what I mentioned to you in the question 13, when I talk about kinetic energy, I'm looking at temperature. Okay, high temperature, high kinetic energy, constant kinetic energy, constant temperature. So if I'm looking for greatest kinetic energy, I'm actually looking for the highest temperature. So basically, the answer is just asking you to look at which of the object has the highest temperature here. Okay, so if you look at it as temperature-wise, you actually have here 100 degrees Celsius. The moment you see the highest temperature, 100 degrees Celsius, that's the answer already. Okay, because kinetic energy is proportion to your temperature. High temperature, high kinetic energy. Okay. 100 megahertz, okay, 1500 megahertz, okay. I would say most students know that frequency. Hardly, maybe one or two students may have misunderstood it. Okay, megahertz, the moment you have the unit hertz, exact, it refer to the frequency. Okay, not the period, not the speed. Now for question 16, okay, question 16, take notes. Okay, when we talk about amplitude, okay, when we talk about amplitude, it's always from the crest to the equilibrium position, or sometimes we call this the middle line. From the crest to the middle line or the equilibrium position, or sometimes it's from the minimum to the equilibrium position. Okay, so this is something I would say is exactly the same as your math. Okay, the amplitude of the graph that we are looking at. Then after that, for period, between two crests, okay, it's always what we call your period. Okay, sometimes between two crests is referred to your wavelength. Why? Because we are looking at a displacement distance graph. Okay, if it's displacement time graph, the time give you one cycle time is actually referring to period. If it's displacement distance, one cycle for distance, it actually means wavelength. So you must look at what graph am I looking for. So that's why the answer for question 16 is actually A, not B. Yeah? A, because I give you displacement time graph. If you choose B, you have to make sure that the graph given is actually displacement distance. Then one of the hidden thing, or one of the pattern that we usually see in MCQ is we actually ask the students to comment about the speed. Okay, just to take note, when we talk about speed of wave, okay, remember same medium, the important thing is same medium. Okay, if I have different wave, okay, but they are traveling in the same medium, air, let's say air. Okay, same medium. Okay, if the wave is traveling in the same medium, the characteristic that I have is actually all the waves will have actually the same speed. Okay, that's the characteristic of the medium. If you have the same medium, if the air or the wave is in the same medium air, they will all possess the same speed. Okay, if you have talking about water, if the wave is traveling in water, okay, then you will have another number, the speed will be another value. But any wave that travel in the same medium will actually has the same speed. Okay, so your medium actually control your speed in this sense. 17, the electromagnetic spectrum. Okay, remember you have to remember the arrangement of the waves, the electromagnetic spectrum, gamma ray, X-ray, infrared, ultraviolet, all these. You have to know which is what the arrangement. And usually the common thing that the common question that we ask you is, I will arrange all these ray in terms of wavelength or in terms of your frequency. So same thing, if I ask for frequency or if I ask for wavelength, it's always increasing order or decreasing order. Only these two pattern, I would say. Now, of course, if you look at electromagnetic spectrum, other than looking at the positions, the other thing that we always frequently ask students is the uses of all these electromagnetic waves. Right? For example, gamma ray, what can gamma ray be used for? What can visible light be used for? What can be infrared light? What can be infrared radiation be used for? Okay, so the uses, okay, and advantage and disadvantage of all these waves, where you have to know them by heart. Okay, we have statement 18. Okay, it's true about the wave itself. Take note, the wave that we're looking at, all these waves are transverse wave. Oops. Okay, all these are transverse wave. Transverse wave, or what we call EM spectrum, they always have this property. You have a lot of properties pertaining to EM waves. Okay, one of them you have is all the waves actually travel at this speed in vacuum, 3 times 10 to the power 8 meter per second in vacuum. Okay, these are the characteristics that they have for EM waves, and they are transverse wave. Okay, so these are the waves. So the property for the wave, you have to actually to know them to get familiar with them. The other wave that we are talking about is your longitudinal wave. Okay, longitudinal wave is, I would say, it's easy because there's only one version of it. With longitudinal wave, there's only one one example of it, and that will be your sound. Okay, so if you see sound wave is actually a longitudinal wave, and literally any other wave, you have a high chance, 90% chance that it is a transverse wave. Question 19, okay, the formula V equal F lambda. I will not dwell too much on this. Okay, this is a classic just an example of substituting the values into the formula. Okay, I given you frequency, which is F. Speed is given is V. I ask for lambda. So if I given you frequency, okay, I given you speed, okay, you definitely can use the formula to find what is your wavelength, which is your lambda. Okay, so you get an answer to be B straight away. Now for question 20, right, resistance. Okay, resistance, length, and diameter. Okay, if you talk about these three factors you have, is a classic example of resistance equal to rho L over A. Okay, resistance, this rho refer to your resistivity. The type of the resistivity will control the type of wire. It be copper wire, steel wire, iron wire, the resistivity will be different. So that value, or this value, resistivity, actually control the types of wire being used. The rest, I would say straightforward, the length and the area. One of the things that you have to pay attention, if you talk about area, like we all know that wires is always like in cylinder shape. Okay, if you talk about area, the formula we are looking at is actually your basic formula for area, with circle pi r square. Okay, so here take note. Okay, if you look at the mathematics, it's like when we talk about radius, if the radius here, radius, there's an r square value here. So literally I'm looking at is, if you look at area, area is pi r square. Okay, one of the common questions in MCQ or even in structure we like to do is what I will actually tell students what happens if I change the radius. Okay, if I radius, remember, because of the pi r square, because of this square here, if my radius increase by 2 times, okay, take note, if my radius increase by 2 times, okay, literally because of the square value here, I can actually say my area actually become quadruple. It become 4 times because of the square, because of the pi r square. So if you look at it in terms of math, be careful. This is some of the common question that I will tell students saying that the radius actually increased by 2 times, but actually the area actually quadruple, increased by 4 times. Okay, so this is one version of question that can come up. The other version of question that can appear in your MCQ is like what you see on this question, question 20, is I literally give you all the values. Okay, so what you need to do is, if they are the same wire, so literally I'm saying that my resistance, okay, is actually determined by length and area, or to be exact, is the ratio of length and area. Okay, so if I want my resistance to be high, the best thing I want is actually what I call my length must be high, my area must be smallest. Okay, because only when my length is high, what I call the numerator. Okay, my numerator is high, my denominator is small, the ratio of these two numbers, L over A, okay, will be large. And the ratio actually controls the size of the resistance. So if my ratio L over A is large, my resistance will be large. So for question 20, right, there's no, I would say the easiest one is just look at it in terms of math, just substitute all the number inside, after that look at the ratio. But here, be careful, factor that I given you, okay, remember the ratio I'm looking at is actually length divided by area. Area is pi r square. So, but here the question given here, the second column here is not area, it's diameter. So diameter, literally, I need to calculate the area first. So let's say if it's 1 mm, my diameter and my radius actually 0.5 mm. So my radius is actually 0.5 mm. So my area will be pi r square. I need to substitute my radius to be 0.5 square. After that, you press your calculator, you get the respective value for area. Then only when you get the area, then you can find the ratio of length over A. So literally, for question 20, you may want to have another table, another column that looks at area. Okay, they calculate the area for each of them. Then after that, you look at the ratio. So I would say it's slightly tedious. Okay, so that's where you get all the time. Let's say question 1, question 2, question 3. You solve that question in like 10 to 20 seconds. Okay, you have extra timing. That's where you use it on question 20. Because question 20, literally, you need to do a lot of working. Now for section A, paper 2. Okay. Now paper 2, description of graph. I would say students, you have to be familiar to how we describe the graph. For physics, describing the graph, we have a certain way of doing it. Okay, we standardize it to be in a way such that when we ask students to describe velocity time graph, okay, we actually looking for acceleration. The students need to show that they know that they can actually identify acceleration from a velocity time graph and use it in their description. So if you look at the description here, we are looking at is actually let's say AB is this line here. Now the AB, which is a straight line, which is actually what we call your constant speed. But here is actually constant speed, or in terms of VT graph, is what we call zero gradient. And gradient in VT graph actually represent acceleration. So this is how I always remember how to describe the graph itself, because the gradient actually is equate to acceleration. So whenever I see gradient, I'll actually replace the word gradient with acceleration, and I just describe the graph accordingly. Okay, so a common mistake that we're looking at is the question asked for A, B, and BC. AB is the horizontal line. Okay, but a lot of students thought AB is the upward sloping line. A lot of you all thought this is the AB I'm referring to, the first line I'm referring to. Okay, so please read your question carefully. Deceleration of the object. Okay, deceleration, if you look at the graph, deceleration, aka it means it is a negative sloping line. Okay, negative sloping line. And if you look at the question, only section BC is negative slope. So automatic deceleration refer to the line section BC. Okay, and same thing, deceleration. Yes, we know that deceleration has to be a positive number, but we do not have a formula to calculate deceleration. Deceleration always derived from acceleration, which has the formula final minus initial. And the final speed for BC is actually, final speed is actually 0 meter per second. Initial speed is actually 10 meter per second. Okay, so you have to know how to locate your initial and final speed. It doesn't mean that final speed always have to be a big number. Initial speed always have to be a small number. No. Look at the question, look at the time. Okay, so you'll know that if initial speed is 10, okay, there's U is 10, your final speed V is 0. So you substitute into the formula, you get the answer negative 1.25. Okay, and conversely, the deceleration will be 1.25 meter per second square. Okay, and the last part we are looking at is calculate the distance. And like all kinematics, when you talk about distance travel, is always distance under, distance is actually what we call area under the VT graph. Okay, so the area under the VT graph for first 16 seconds. Okay, first 16 seconds, the area I'm looking for is actually here. Okay, first 16 seconds is the area I'm looking for is here. Okay, this triangle and this square, or what I call a trapezium shape. So literally, I'm looking for the area for this shape here. If you know the formula for trapezium, by all means, go ahead and use it. If you don't know, okay, don't worry. Okay, you can still break down the trapezium into what we call a triangle and a square, and you can use the basic formula triangle and square to find the to find the area. Okay. Give me a minute. Oh, okay, here you go. Okay, so the area is here. So take note of the working. Okay, then you arrive at answer 140. Okay, I will not say it's difficult. Okay, but please try to refrain from using the formula distance divided by time. Distance divided by time is what is usually referring to constant speed motion. In upper sec, okay, in your sec 3 and sec 4, or what you call your year 8 and 9, okay, your motion of the object is actually, it can be constant, it can be increasing, it can be decreasing. So there's no fixed motion for it. So that's why speed equal to constant distance divided by time, this formula is actually not applicable. Okay. So take note of your kinematics. Okay, we know what to do. Okay, when dealing with kinematics. For question 2, okay, question 2 I would say is quite straightforward. Most of us we are able to get the answer correct. So I will not dwell too much on this. Okay, it's a basic density question. Okay, question 3, you are given diagram on the left. This is the one that's given. Okay, the diagram on the left is the one that's given to you. Okay, now when you look at the object swing freely and after that coming to rest. Okay, when I say swing freely and coming to rest, there are a few clues behind this statement. Swing freely means that whenever it swing, when swing freely means there is no resistance, there's no friction. And when talk about swing freely and coming to rest, okay, it means that the pivot, okay, and the CG, there's a relationship between the pivot and CG. Okay, if you are swinging freely, okay, you will always have this phenomenon whereby the CG is always at the lower side. Using your CG is always below the pivot. Because if I'm able to swing freely and eventually I come to the rest, this statement will tell you that the object is actually looking for a stable equilibrium position. And for stable equilibrium position, the CG has to be at its lowest point. So automatically I will know that the CG has to be below the pivot. And if I'm not swinging anymore, it means that my CG is actually directly below. Okay, not just below, it's directly below. Okay, whereby the perpendicular distance is actually 0. So if you look at the new object here, my triangle, you find that my CG and the pivot, they will actually form a nice straight line. Okay, this is what I mean by directly below. Okay, they will form a nice straight line. Okay, cutting through. Okay, my CG is always directly below the pivot. Okay, and same thing, CG, your weight act through the CG and your weight is always pointing downwards. Okay, so take note of the drawing. Okay, so when we talk about swing freely, okay, there are a few conditions behind it. Okay, and remember the condition, it has to be CG is always below the pivot because it's always looking for the most stable position. And it has to be directly below because swing freely coming to rest means there's no more moments really. Okay, there's no more clockwise or nor anti-clockwise. So the perpendicular distance has to be 0. Okay, and this is what I mentioned. Okay, and true enough, okay, the second part of the question asks you why does the object always remain at this position? Okay, and it has everything to do with the moments being perpendicular distance being 0. Then as a result, there's no turning effect or no moments acting on the object. It will not swing anymore. Keywords when you're looking at the explanation, okay, remember always to write the keyword, okay, perpendicular distance. Okay, perpendicular, don't just write distance. Okay, because when you talk about moments, I want the shortest distance between the pivot and the force itself. And that shortest distance is actually what we know as perpendicular. Okay, two reasons. Okay, lower CG broad base. Most of students, you actually know the factor to increase stability, which is good. Okay, it means that you actually read through the notes and memorize some of the important things. Now, question 4 is a vacuum flask. Okay, vacuum flask is a classic example whereby all the 3 modes of heat transfer actually come into play. Okay, now take note of, but when you write or describe the uses of each of the component of thermal flux. Remember the usage of stops, reducing. Okay, it has different meaning. For example, for conduction, okay, for vacuum flask, you can write, how do I stop conduction? Definitely, I can use vacuum. Okay, because with vacuum, conduction cannot take place because conduction needs a medium, need particles. So if you use vacuum, you have to make sure that you mention stops conduction. Okay, totally stop, 100%, nothing at all. You cannot use the word reduce. If you say reduce, right, it means that the conduction is being reduced. There is a bit of heat loss through conduction. There is still conduction, but it's just very low. But when you talk about vacuum, whereby there's no particle at all, you can't have conduction being set up. So that's why we have to pay attention when we talk about vacuum. The usage of the word reduce or stop is actually very important. Other than vacuum, okay, there are other components. Remember, for conduction, we are looking at the medium itself, the presence of air particles and presence of particles, and the particles in terms of different arrangement, it gives rise to a solid, liquid, gas. So if I use a solid here, it can be a plastic support. Okay, I use a plastic support. Why? Because plastic is a bad conductor. Okay, this particular material, okay, does not allow heat to conduct through easily. If I don't want plastic support, I can look at glass wall, because glass is a bad conductor also. Okay, literally the medium itself. Conduction refer to the medium. Okay, so the keywords or the component that I'm looking at is I'm looking at the medium itself. I'm not looking at the color, I'm not looking at the thickness. Okay, so I'm looking at the medium itself. Convection, there's only set to say. Okay, convection, but there's only one section here in the sense that convection, we talk about hot, rise, cold, sink. If I want to reduce convection or want to stop convection, I actually have to stop the hot air from rising. That's the only way only. And to do that, there's actually two things that we're looking at. So you can actually talk about the cap, the plastic lid being on top, or the cup on top. Both serve the same purpose. Okay, the cup and the plastic lid actually prevents the hot air from rising. So if the hot air don't rise, the cold air can't sink. And if hot don't rise, cold don't sink, I will not have what we call a cycle of convection current setting up. And because I don't have that cycle, I will not have heat loss through convection. For radiation, take note, radiation, we are looking at the certain properties of, for radiation, certain properties of the particle, particularly in terms of colors, texture, rough and smooth, then followed by size, big and small, then followed by the temperature of the liquid with respect to the environment. Okay, for example, if I'm hotter than environment, I will lose heat faster. Or if I'm lower than environment by a great deal, I will actually absorb heat at a much faster rate. Okay, so if you look at color and texture, okay, the easiest one I would say is the glass itself, the shiny glass. Okay, the shiny glass, okay, the word shiny refer to texture. Okay, so texture, glass surface, glass area being shiny, definitely it will be a poor emitter, or you can say the outer glass being a poor absorber. Okay, now take note, how do you know it's an absorber and emitter? Okay, the important thing here is when the question say hot water. When I mention hot water, you have to take note as which area or which region is hot, because heat transfer is always from hot to cold. Okay, it's always from hot to cold one. So if the vacuum flask, the interior of the vacuum flask is hot, is hotter than the environment, definitely the heat will travel from interior to exterior. So the direction will be from inside to outside. So that's why I will know that the vacuum flask is actually losing heat. But on the other hand, if I replace the word hot water, if I use cold water, it will mean that the interior of the vacuum flask is actually colder than the environment, than outside. So heat will travel from hot to cold. So now the exterior is hotter. So the heat travel from hot to cold. So now the heat will actually travel into the vacuum flask, or aka the water or the interior of the vacuum flask is absorbing the water. Absorbing the heat. Okay, so direction, okay, you have to be careful. So because now I know that interior is hot, so the travel will be hot to cold, heat travel from hot to cold, or sometimes I would say from inside to outside. Okay, so that's why I know that the interior of the glass, okay, or the exterior of the glass, which section is absorber, which section is emitter. Okay, so you have to actually be very, very clear about which section is being an emitter, which section is absorber. Now for section B, okay, the format for section B is 3 questions, choose 2. Now, an advice for all students, which I always tell them to actually adopt, is actually before you choose the 2 questions, remember to read through all the 3 questions first, because it doesn't mean that the first question you see is always the easiest or is always the hardest. It also doesn't mean that the last question is always the easiest or is always the hardest. Okay, so read through all the 3 questions first, then decide on which 2 questions you are more confident with. Okay, in the sense that if layman term, I would say just choose the question that allows you to score the best. Okay, you need, let's say for example, like question 1, electricity. Question 3 could be thermal property. It could be 2 topics that you don't like one. You're not good at it, but you still have to attempt. You still have to choose the best of the worst. Okay, it's the best of the worst. If you can choose the best, 2 best, or that would be the most ideal case. But no matter what is all the 3 questions, you have to read through all the 3 questions first before you attempt any question. Because let's say, for example, you tried the first question because it's being the first question, you just do it. But you realize that question 1 is actually, the question 1 is actually, the first question is actually the worst question. Your question 2 and question 3 is actually one of the better question. So if you attempt question 1 first, right, you have actually wasted like maybe 10 to 15 minutes of your time. Okay, so control your time, which make use of your time wisely and choose the most or the best questions, okay, in sections B. And usually the best question actually decide whether you have a good grade or not. Now for question 5, okay, question 5, I would say it's a simple question because I've gone through this particular arrangement of resistor quite often because it's one of the hot favorite if you look at circuit, okay, whereby you have 2 resistors in parallel, which is the green color one, this in parallel, then followed by the resistor in series. Okay, now adding of resistance, okay, 2 resistors in parallel first, okay, you have to add them together, which is here. Okay, the formula, you have to remember the formula. Some of us or some of the students actually forgot about the formula and start to just add 6 plus 12. Okay, start to add them like a series arrangement. It doesn't work that way. Okay, for parallel arrangement, remember it's 1 over R. 1 over R. So eventually you end up with 1/4. And when you get a 1/4, remember to flip on what we call to get the inverse, because I'm not looking for 1 over R. I'm looking for R parallel. So that's how I get my 4 ohm here. Okay, then after that, in series, you just add up. So it's 4 plus 2. Okay, remember for answer wise, final answer in physics is always 2SF. Okay, sometimes you can leave it in 3SF. Remember to write units with units. Okay, intermediate answer like 4 ohms. Okay, you can leave it in any SF, you can leave it in fraction. Okay, but ultimately you must remember to write units because every value I get, it always have a unit. Okay, because if not, the marker will not know what you are finding. For current, okay, current flowing through the 2 ohm resistor. Okay, there are a few ways to do it. Okay, so after part 1, I actually has the total resistance. Okay, I actually have the total resistance here. Okay, so now the total resistance, the wire, the current traveling here is actually my total current. And total current here, I would say is in this diagram, this is my total current. Okay, my total current returning. The total current returning. Okay, so the most straightforward way to find the current flowing through the 2 ohm resistance. The current flowing through the 2 ohm resistance is actually based on diagram, is actually your current total. Okay, so basically current flowing through 2 ohm resistor is basically asking you to calculate the total current flowing in the circuit. So the easiest way to use is to use Ohm's law, V equal to IR. Okay, V equal to IR means V equal to IR. If I need total current, I will definitely need total potential difference and total resistance. Okay, total resistance given already is in your part A answer. Okay, which is here. potential difference is the battery. Okay, total potential difference is actually the battery source, which is 1.5. Okay, so if you have the value, okay, you substitute, you will have this math formula 1.5 divided by 6, and you get answer to be 0.25 straight away. Okay, so remember what values you are using, because circuit is, I would say like 70% of circuit involve math, but the math the formula is always the same. V equal IR, V equal IR. Okay, your Ohm's law. But at Ohm's law is applied at different position, you require different factors. So you must know where to get your variables, where to get your numbers, so that you can get the correct answer that you need. Electric charge. Okay, electric charge. Okay, the formula Q equal to IT. Yeah, this formula, I can see that most of you remember the formula. You can actually do it with ease. Okay, there are a small portion of you who forgot the formula. Instead of Q equal to IT, you write Q equal to I over T. Yeah, okay, you forgot about the formula. Okay, so please take note on the formulas. Okay, there's no formula sheet in physics, so you have to remember the formula. The other common mistake I see is that when we talk about QIT, I remember SI unit, the factor that is always in physics formula, the variable that you substitute inside the formula is always has to be SI unit. So if I give you 1 minute, okay, 1 minute is not SI unit. Minutes of time is always in seconds. So you must change this 1 minute to 60 seconds before you substitute it into the formula. Because I would say 90% of the physics formula require SI unit. So you must know your SI unit, and you must be alert whenever I give you variables that is not in SI units. So you have to actually change it. Potential difference of resistor X. Okay, resistor X. Where is resistor X? Okay, resistor X is here. Okay, this is your resistor X. Okay. Now, most common mistake students make is actually everybody thought the potential difference is of resistor X is 1.5, which is wrong. Okay. 1.5 volt, if you look at it, 1.5 potential difference 1.5 volt is across the total resistance. So it's not just across resistor X, it's across all the resistor. Okay, so resistor X will definitely have a potential difference less than 1.5. Okay, because resistor X is just part of the component only. Okay, it will take up a portion of the potential difference. Confirm not 1.51. Because 1.5 is the total resistance. Okay, so how do you find the potential difference of resistor X? Okay, now let's take a look at this. Okay, so the easiest way we look at is I know that, okay, if you look at parallel circuit, the potential difference across 2 ohms, let's say I give this V2, must be equal to, I will not say equal lah, potential difference of across 2 ohm resistor must, okay, and the potential difference across the parallel branch, okay, these two potential difference must add up, and it must give you one number. It must give you 1.5 because they are part of the circuit. So in terms of circuit arrangement, what we are looking at is actually potential difference of the parallel resistor. In this case, okay, the potential difference of the parallel. Let's say this is my 2 ohm, V2. I need, this is my R parallel. Okay, so I will know that the potential difference across my parallel branch and the potential difference across my 2 ohm, the sum of these two potential difference will definitely add up to be 1.5. Okay, so all I need to do is if I'm able to find V2, if I'm able to find V2, and I know the total voltage is 1.5, I will be able to find my potential difference of my parallel branch. And why do I want to find parallel branch? It's because under this parallel branch, I got resistor X and I got resistor Y. And I know that if I know the parallel branch of potential difference of the parallel branch, I will definitely know the potential difference of X and potential difference at Y. Because for parallel branch, one of the property for parallel branches is that the potential difference is always the same. Okay, so this is where I try to solve the question using the basic properties of series and circuit. Okay, so what I set out now to do is I want to find potential difference of V2 first. Okay, so I want to find V2 first. If I can find V2, I can find V parallel. And the moment I find V parallel, I will actually have the potential difference across X. And this is what my working is doing. Okay, I start to find V2 first. And V2, if you use Ohm's law, right? If I need V2, V equal IR. If I need V2, I definitely need current across 2 ohms. I definitely need resistance of 2 ohms. Okay, because remember Ohm's law is like a selfish rule. Right? If I need component 2, I need everything about component 2. I need potential difference of component 2. I need potential difference of component 1. Okay, and I need the resistance of component 1 also. Okay, then after that, I get my V2 to be 0.5 and 1.5. 1.5 is the total voltage minus 0.5. I will get 1 volt for X. Okay, and similarly, if I have the potential difference of X, I will have the potential difference of Y. Because they are parallel branch, they are always the same number. Okay, and I will be able to find the current flowing through resistor Y using V equal IR. Question 6. Question 6 is thermal property, whereby you look at explanation. The explanation I given to my students, some of the standard, it's a standard explanation, standard answers with standard keywords. So you have to remember at which stage, okay, what are the keywords that's available, what are the keywords that you must write. Okay. Now for substance here, okay, the 4 stages, okay, this will be heating, this will be melting, then this will be heating again, and this will be boiling. Okay, so remember the 4 stages, and likewise, I mentioned before, each of the stages, there are respective keywords which I given you. Okay, please know the keywords, please know how to use. Okay, and primarily these keywords revolve around the kinetic energy of the particle and the potential energy of the particle. If you talk about kinetic energy, you have to take it with the temperature. Okay, if you talk about potential energy, you have to take the intermolecular forces. Okay, plus you have talked about the change in state, whether it's solid to liquid or liquid to gas. Okay, only exception here or only extra thing that you take note is when you talk about boiling. When you talk about boiling, okay, you have to talk about potential energy. You have to talk about intermolecular forces. You have to talk about change in state, and you also have to include something called pressure, work done against pressure, or what you call you push back atmospheric pressure. Okay. Okay, because for gas to roam around, to diffuse through the environment, for gas to move through the air molecules, he definitely need energy to push back the air molecules in the air, and so that the gas molecule can actually come out, can actually move around the environment. Okay, so for pushing back atmospheric pressure, this only applies to where? This only applies to boiling. Okay, so usually what we have is the blue color one. 1 and 2 actually refer to boiling and melting. These are the phases. Okay, the exact keywords for each of the phase, okay, I actually included in my thermal property chapter. So if you look at my thermal property videos, okay, you will find that I give you a list of keywords which cover all the 4 stages. So you might want to take a look at it and do a revision on the keywords to use, because the keywords that I use in that particular video is actually used to answer question C. Okay, this answer here is actually appeared in my video for in thermal property. It's actually one of the standard keywords or standard explanation that we always ask students. Okay, which section of the substance is X is in liquid state. Okay, liquid state refer to CD. This one is all the 4 phases. You have to know your 4 phases. It rhymes with your chemistry also. Arrangement of the particle at X at B. Okay, remember B at B here. Okay, remember at B here is the end of the heating, the beginning of melting phase. Beginning only at the beginning. So which means at B here, I am actually still a solid particle. I'm still solid only. I'm about to melt. I'm starting to melt. I have not do anything yet. I'm still a solid. So actually B here actually refer to the object is still in solid phase. Okay, melting is a process. Melting is a process that takes time. Okay, so the from B to C, okay, from B to C is actually melting. And B to C melting means solid. I'm at B is solid. At C, I'm melted. I'm completely liquid. So in between B and C is like a mixture of solid and liquid. Okay, so you must know where is your phases, where are your phases, where are the keywords, what are the state of matter for each of the 4 phases. Okay, which is we consider as facts. Okay, so you need to get your facts right, get your keywords correct, and get your sequence correct, okay, before you can answer any questions. Boiling and evaporation, surprisingly, okay, a lot of students actually have no idea what is evaporation and boiling. I wonder why. I thought, okay, so boiling and evaporation, there are similar things between them. Similar thing as in what? Boiling and evaporation involve the liquid turning from liquid to gas. Okay, a lot of students wrote, okay, boiling refer to solid, liquid to gas, but evaporation referring to where a solid to liquid is totally different, totally off. So 2 differences, okay, it's in the book, in the textbook. Okay, so you can just take any one of them. Usually I just take the shortest, okay, to avoid any typo, spelling mistakes, all this. Question 7. MGH, energy, MGH, typical formula. Okay, energy is MGH, kinetic energy is half mv square. First cut, the formula you must know. Okay, the object dropping down. Okay, second thing you have to pay attention is the use of SI units. When you talk about energy, MGH half mv square, okay, the formula that we are using, okay, it has to be in SI units. So you have to check whether the mass is in kg, whether the height is in meter, whether the speed is meter per second or not. Okay, because it always has to be SI unit. Okay, once you have it, I would say MGH, you just substitute the number, you get the answer straight away. Okay, it's a classic example of ball being thrown down, ball being dropped, sorry. So it dropped all the way, okay, before hitting, before hitting. Okay, so I have potential energy. Then after that, before hitting, all the energy is being converted to EK. Okay, and this is your typical example of conservation of energy, 100% conserve. Okay, so which means your potential will be converted to your EK. That's why part B, I know the answer is actually 3 joules straight away, because energy is being conserved. And likewise, with kinetic energy, I can actually calculate the velocity using half mv squared. Okay, I would say it's a simple math manipulation. Okay, you have to remember the formula. If not, you cannot do anything about it. Now, whether the ball will bounce back to the original height here. Now, from part A to part C, right, you'll find that, from part A to part C, you'll find that there's no mention of air resistance, etc., etc. And in fact, you actually use conservation of energy, whereby you use potential energy equal to kinetic energy, 100%. So the conversion is 100%, aka no losses. Or sometimes we call this ideal stage. Okay, so it's ideal. So which means energy is being conserved, which means if I can convert from EP to EK, I definitely can convert back from EK to EP again without any losses. And because I can convert from EK to EP to EK again, 100% conversion, I will be able to bounce back to my original height again. Okay, because energy is 100% conserved. Okay, there's no mention of losses. A lot of students, you say that there's losses, there's friction, there's air resistance, but there isn't any mention of that in the question. Okay, but I do know that some questions in the 10 series or in the practice paper, we always like to say that, oh, the ball is not being able to bounce back in real life because there's air resistance. But read the question first. The question has no mention of anything about air resistance. And in fact, it actually go from part A to part B and part C. Part A to part C is still ideal phases. Okay, so there's no losses here. So read the question, don't jump the gun. Okay, don't assume anything. Okay. Now, if the heavier ball is dropped from the same location, okay, will the speed remain the same, increase or decrease? Okay, take note, energy is conserved. Okay, if I have a larger mass, if I go up to the same location, yes, I will definitely have a higher potential energy, confirm, because I am a bigger size. Even though it's at the same height, I will definitely gain more potential energy. But then when I drop it down with a higher potential energy, I will not get a higher kinetic energy, because now for me to accelerate, for this heavy object to accelerate to the same speed, because it's heavier now, I will need to spend more energy to push it to increase the speed. So by the time I spend all the extra energy, I can only increase the speed back to its original number only. So that's why we talk about conservation of energy in dropping cases, okay, whereby we have EP equal to EK. You'll find that because even though I'm a bigger object, I gain higher potential energy, but because I am bigger size now, I actually needs more energy to move. And because I need more energy to move, the extra energy I have from potential energy is actually being used, okay, to push up my speed back to the same number again. So as a result, you'll find that the speed actually has no change. Even though my potential energy is higher now, but I actually need more energy to move now. So the extra energy that I gain because of my masses is also causing me to lose more energy in terms of kinetic energy. Okay, the other way of explaining is you look at it in terms of math. If you look at it in terms of math, on the left side of the equation, you see mgh. 100% convert means my potential energy is converted to kinetic energy, which is half mv squared. Okay, if you look at it in terms of math, you'll find the left side of the equation got m, right side got m. You'll find that if you look at it in terms of algebra, m and left side and right side, they are common factor. So I can actually remove m straight away. I can actually cancel m. Okay, and my final equation will be gh equal to half v squared. In other words, my velocity actually depends on my gravitational field strength and height of the object only. It doesn't depend on my mass. Okay, when we look at algebra, when we say that both m can cancel, mass can cancel, when we talk about cancellation of factor, in physics, it means that the factor is being cancelled. It means that the factor is actually an independent factor. My energy or my motion doesn't depend on that factor, and that factor happens to be mass. So in terms of math, when we talk about cancellation of factor, it means that the situation doesn't depend on it. So that's why I can say that it is actually independent of mass. Okay, so that's where the math and the science actually meets together, okay, to explain the same thing. Okay, and this is the last question for this particular paper. Overall, the paper, I will not say is difficult. There are some tricky part, like example, like this particular question E, 7E, which is quite slightly more tricky. And there are certain questions like question 6 is actually a standard question that students need to know actually. And in fact, it's so standard that every practice paper, whenever it come up, thermal property is always the same pattern, same style. Okay, so in a nutshell, for this paper, okay, the only takeaway I have to tell students is that you have to get all the facts, the topics, the keywords actually sorted out before sorted out before you take your paper or do any revision paper. Okay, for the revision to be effective, your content, your keywords must be there. So that every paper that you do, every revision paper that you do, it actually highlights some of your mistake that you make, some of the gaps that you make, so that after every revision paper, you can actually use the gaps and you know where are your gaps, you can actually touch it up so that the next paper you don't make the same mistake again. Okay. If you need any other information that is I have not mentioned, okay, feel free to drop me an email. Okay, or if I have said anything wrongly or I misrepresented anything, or just do let me know also. Okay, because I do make mistakes sometimes. Okay, drop me an email or leave a comments, leave your feedback in the comments bar below. Okay, if not, I will be uploading, I think, 2 more papers in the next few weeks. Okay, some revision paper that I managed to get my hand on. Okay, if you need any updates of the video, okay, remember to subscribe to the channel. Okay, then take note of the notification bell so that whenever I upload, you actually get an email or an alert on that particular paper, just in case you need it. Okay, for the paper, the blank copy is in the description bar below in my Google Drive. Okay, feel free to use it. Okay, and okay, all the best for your exam.